Hello everyone, and welcome to the lecture on the Knight's Tour problem. So in this section in this lecture, we're going to explain the Knight's Tour problem, what that puzzle is. We're going to see how we can use graphs to set up the solution. We'll view a solution in Python and then continue on to get a more general view of depth first search. Now just keep in mind, as far as the breadth first search and depth first search, so BFS and DFS, in the previous lectures we saw some basic puzzle, that word ladder puzzle, as just an introduction to an idea of why we would want to have BFS. In this lecture, we're going to see the Knight's Tour graph problem as an idea of why we need DFS. After this lecture and the next one, what we're actually going to do is have 3 lectures in a row where we fully code out and do a live code walkthrough with explanation, again of a graph implementation, an implementation of BFS, and an implementation of DFS. So while you will see code as just an image throughout these slides, keep in mind that we're actually going to live code all the algorithms in the graph overview again later on in the section of the course here. So don't worry about having to code everything that you see right now. This is just basically to give you some ideas of why we need DFS. So let's go ahead and continue on. So what is the Knight's Tour puzzle? Well, the Knight's Tour puzzle is played on a chessboard with a single chess piece, the knight. And the object of the puzzle is to find a sequence of moves that allow the knight to visit every square on the board exactly once. And you don't need to know too much about chess to get this puzzle, but what we're going to do is solve the problem using 2 main steps. One is to represent the legal moves of a knight on a chessboard as a graph. And then we can use a graph algorithm to find the path of length, rows times columns, just -1, where every vertex on that graph is visited exactly once. So let's go ahead, and check this out. So in case you're not super familiar with chess, a chess again is an 8x8 board. This is just a subsection of that board, and you have this knight. And the knight piece can move in an L fashion. So all the dots here are legal moves for the knight. So you'll see it has, here's an L, so 3 then 1, 3 then 1, 3 then 1, and that's how the knight can move. So those are all the legal moves for the knight in this particular subsection of the board. And you can see that we can represent this as a corresponding graph. So now we want to know really how we can build out this full graph. And we can actually use that using this function here, the knight graph function. So what this is going to do is the function makes one pass over the entire board, and at each square on the board, the knight graph is going to call a helper function called generate legal moves, or gen legal moves, which is actually on the next slide if you want to check that out at the same time. But basically what it does, it just creates a list of legal moves for that position on the board. Then all the legal moves are then converted into edges in the graph. Another helper function, which is called position to node ID, or POS to node ID, converts a location on the board in terms of a row and column into a linear vertex number, similar to the vertex numbers shown earlier in this slide. And then if we just take a quick look at that generate legal moves function, basically what this does is it just takes the position of a knight on the board and generates each of the 8 possible moves. And then it has another helper function, legal coord, or legal coordinate, and it just makes sure that particular move that is generated is actually still on the board. So you have board size here, so 8x8 or whatever, and you just want to make sure that the legal move doesn't bounce the knight off the actual chessboard. So again, these are in the Jupyter Notebook that goes along with this lecture, but don't worry too much about them. It's just for this specific puzzle. And what we're going to do later on is actually generate, or implement, I should say, in Python, a very specific DFS and BFS after these next 2 lectures. So continuing on, if you want to know what all the possible board moves look like after you built the graph, it looks something like this. And this is something we'll revisit later, but this basically just shows the complete graph of all possible moves on an 8x8 board. So there's exactly 336 edges in this graph. And what you should notice is that the vertices corresponding to the edges of the board have fewer connections, right? Which are legal moves. So example, these are the vertices of the edge of the board, and they have less legal moves, which makes sense because your knight would then bounce off the board. So you can only really do 2 legal moves from the corner, which makes sense. And once again, you can see how sparse this graph is. So the graph is fully connected. If the graph was fully connected, meaning every node was fully connected to every other node, there would be 4,096 edges. but there's actually only 336 edges. That means if we were to try to use an adjacency matrix to fill out this graph or represent this graph, it'd only be about 8% full. So definitely, for larger graphs, the adjacency list is the way to go. So that's just a little reminder and throwback to that old lesson we had. So continuing on, what we're going to do is the search algorithm we're going to use to solve the Knight's Tour problem is called depth first search, or DFS. And whereas BFS algorithm discussed in the previous section builds a search tree one level at a time, the DFS algorithm will create a search tree by exploring one branch of the tree as deeply as possible. So in this section, again, we're going to look at two algorithms that implement that depth first search. The first algorithm we're going to look like is directed really particularly to this specific puzzle, the Knight's Tour problem, and it explicitly forbids a node to be visited more than once, which is exactly what the Knight's Tour puzzle was, right? We wanted to visit every position on the board exactly once as a knight. Later on, we're going to discuss a more general DFS, which we'll do in the next lecture. So the depth first exploration of the graph is exactly what we need in order to find a path that has exactly 63 edges. We will see that when the depth first search algorithm finds a dead end, which is a place in the graph where there are no more moves possible, it's going to go back up the tree to the next deepest vertex that allows it to make a legal move. And this is for the particular algorithm for solving the Knight's Tour puzzle. So the Knight Tour function, which is actually here on the next slide, but it's going to take 4 parameters. N, which is the current depth in the search tree, takes in path, a list of vertices visited up to this point, U, which is the vertex in the graph we wish to explore, and then limit, which is the number of nodes in the path. And you should note that the Knight Tour function, in this case, is recursive. So let's go ahead and explore it here a little further in depth. So you'll notice what happens is that our function again is using colors to keep track of which vertices in the graph have been visited. So unvisited vertices are colored white, and visited vertices are colored gray. And again, if all the neighbors of a particular vertex have been explored, and we have not yet reached our goal length of 64 vertices, then we've reached the dead end. And when we reach a dead end, we have to actually backtrack. So backtracking happens when we return from Knight Tour, that Knight Tour function, with a status of false. So if you return with a status of false from the Knight Tour function, meaning done was never set equal to true, it means you have to backtrack. And so in the BFS, the breadth first search, we use a queue to keep track of which vertex to visit next. And since depth first search is recursive, we are implicitly using a stack to help us for backtracking. So when we return from a call to Knight Tour with a status of false, which happens in this line, right here when you say done is equal to that recursive call of Knight Tour. So when you return from a call to Knight Tour with a status of false, you're going to remain inside this while loop because you're saying and not done, right? And you're going to then look at the next vertex in that neighbor list object, which is right here, NBR list. Remember, that's just a list of getting the connections. So let's go ahead and look at a simple example of the Knight Tour in action. And I'm going to show you some figures of what you can check out. So let's go ahead and jump to the figures. And if you downloaded this resource PowerPoint presentation, everything I just said is in the next couple of slides. So we're going to go ahead and jump forward to right here, this Knight's Tour example. So we're going to do is start at node A, and the nodes adjacent to A are B and D. So we can see this is a directed graph already. And since B is before D alphabetically, the DFS is going to select B to expand next. So let's go ahead and show that. So we've selected B to expand next to. And then exploring B happens when that Knight Tour is called recursively. B is adjacent to C and D, so then Knight Tour will elect to explore C next, which will be the next one. So now we're exploring C. However, as you can see, node C is a dead end with no adjacent nodes. So if you look at where the edges are pointing, it doesn't point outwards from C. So we've reached the dead end here. So now that we've reached the dead end, what we have to do is backtrack. So what we then do is set C back to white, and the call to the Knight Tour function will return a value of false. the return from the recursive call effectively backtracks the search to vertex B. And the next vertex then to the list to explore, since we already did C, is going to be D. So then we go ahead and explore D, and we do that with a recursive call to node D. And from vertex D on, what the night_tor function is going to do is continue to make recursive calls until we get to node C again. So it makes another call here. E, F hasn't been explored, so we go to F, and then finally we've reached C. And by this time, this last time that we reach C, what we'll notice is that N marker is going to be less than the limit, meaning we've already exhausted all the nodes in the graph, and that at this point we can return true to indicate that we've made a successful tour of the graph. And when we return the list, the path is going to have the values A, B, D, E, F, C, which is the order we need to traverse the graph to visit the node, each node exactly one time. So what does that actually look like if you were to try it on a 8x8 board? Well, it would look something like this. So this is the path that a knight would have to take in order to visit each part of the board exactly one time. So there's actually many possible tours, and some are actually symmetric. And with some modification, you can actually make circular tours that start and end at the same square. So there's many solutions to this problem, but you can see that using a graph, especially a recursive searching algorithm to that graph, is a great choice for trying to solve this puzzle. So that's the basic idea. Up next, what we're going to do, we've gotten this brief overview of that special use case. We're going to try to discover what general depth first search looks like, and afterwards we're going to do a full live code walkthrough of all the implementations of a graph, breadth first search, BFS, and then depth first search, DFS. Okay, thanks everyone. Go ahead and review this lecture, but this is basically just to get you a general idea of what you can use this for. All right, thanks, and I'll see you at the next lecture.